Alright, well this is it, the final video of single variable calculus. In today's video we are going to finish off our studies of calculus by talking about polar lengths. So we discussed in the last video polar areas. So basically if I had a curve, I could divide it into small little angular subsections and sectors, and we could use the sector formula and then integrate over it to find the area under that polar curve with respect to the angle. Alright, so now what we want to do is we want to discuss length. So how do we find the length? So I'm going to go through a bit of a derivation, bring back parametric equations a little bit, and then we're going to do an example. We're going to do an example with a calculator because I really want to reinforce that at this point we know how to integrate functions. We have techniques of integration. There are some functions, however, that we really don't want to integrate, and we have tools that can help us solve that when it is faster. But the main idea is that we're getting the application of the polar length formula more than anything else. All right, so let's discuss polar lengths. So I wanted to derive this, so this is a bit of an interesting derivation. But anyways, we know that in parametric equations, if I want to find the length, I take the integral between some start point and some end point of the square root of the derivative with respect to the parameter squared plus the y derivative with respect to the parameter squared with respect to the parameter. Okay, so now what we can do is we can treat theta as a parameter. So instead of t, so we're moving t to theta. We have some lovely equations that explain to us how theta and x and y are related. So we need to find x dot squared plus y dot squared to find our length. All right, so we're going to find x dot, we're going to find y dot. So we get x dot, using the product rule, get x dot is equal to r dot cosine theta minus r sine theta, y dot is equal to r dot sine theta plus r cosine theta. Okay, so now what we need to do is we need to relate x dot squared plus y dot squared. So we find this squared plus this squared, and then we see what we get in terms of r, and we get, I'm not going to do out all the algebra, you can do that for yourself, but we get r squared plus r dot squared. So thus, we can equate these two expressions so that we can get the length of a polar curve is equal to the integral between a and b of r squared, of the square root of r squared plus r dot squared. So r dot is obviously the derivative with respect to the theta. All right, so now let's try an example. So we want to find the length of 1 plus sine theta with a calculator. I think we already looked at 1 plus sine theta. It's kind of like a cardioid Limassol shape with the dimple kind of going down to the negative y-axis. Anyways, we want to find the length of this. So what we do, and I'm going to let you use a calculator. So all I want is I want you to transfer this problem statement, use the polar length formula, and then once you get the integral between a and b of r squared plus r dot squared d theta, then I just want you to calculate it, and then it's going to spit out some number. Like on a test, they'd probably give you a calculator. If not, the integral that we get is a little bit sketchy, but that's fine. Anyways, so we will get r dot is equal to cosine theta, obviously, and now we can find the square root of r squared plus r dot squared. Get the square root of 1 plus sine theta squared plus cosine squared theta. All right, so now all that's left to do is plug this into our integral formula. So the length is equal to the integral between 0 and 2 pi, so we want one time around because we've got a graph that looks like the dimpled little friend here. And obviously it's defined at all those points, so theta is going to go all the way around town through our cardioid Limassol friend. And now we get the integral between 0 and 2 pi of square root of 1 plus sine theta squared plus cosine squared theta d theta. Right. So now we can simplify this, do all the algebra we can. We get the integral between 0 and 2 pi of the square root of 2 plus 2 sine theta d theta. All right, now this is an integral that looks a bit messy. So what do? Well, we luckily there is something called the TI-84 or Desmos or Wolfram alpha, and you can use that to solve this integral numerically. I would recommend not solving this integral algebraically because it leads you through quite a convoluted solution. But yeah, it really goes to show that we know how to apply our polar length formula. Once we get an integral, at this point, just use the computer algebra system. You've already learned the techniques, you're fine. So anyways, once we do that with the computer algebra system or what have you, we get 8. So we get the length of this cardioid is equal to 8. All right, thank you for watching today's video, and thank you for watching this playlist if you have made it through. A big accomplishment studying calculus, especially these final units with differential equations, sequences and series, and these parametric equations and polar curves. Really big accomplishment. You've learned so much. You've learned the infinite. Now, I would like to say that your thinking about how the world works is changed by learning calculus. You've turned into somebody who looks at the world discretely to someone who looks at it continuously. Calculus allows us to quantify that continuous thinking. So I really thank you for watching our series, and our problem sets are online, and I hope that you find good luck with your studying. Now, I would normally say in the next video what we're going to cover, but now I need to say what we're going to cover in the next course. So in the next course, we are going to be talking about multivariable calculus. So the video structure will be very much similar. The problems will be a little bit more challenging, and we will be continuing on the other course. So just to preview multivariable calculus, we will be covering the two other prerequisite units. This was actually the first prerequisite unit. We parameterize everything. We use polar coordinates all the times in multivariable calculus. But the next two prereq units are going to be 3D space and vector functions. So vector functions will be motion, 3D space, how to parameterize them with vectors.